Think about the materials all around us. The steel in a bridge, the plastic in your keyboard. For the most part, they're pretty passive, right? They just sit there. But what if they weren't? What if the stuff we build with was, well, alive with purpose? Let's dive into the absolutely fascinating world of smart materials. Seriously, just imagine this. You drop your phone and, that spider web crack appears. But instead of a trip to the repair shop, you just watch as it slowly, magically stitches itself back together. This isn't science fiction, folks. This is the very real promise of a whole new class of materials. So what exactly makes a material smart? Well, it all boils down to this one core idea. It's not about thinking like we do. It's about being engineered to do two things perfectly. First, it has to sense a change in its surroundings, and second, it has to respond with a specific, predictable action. That sense and respond loop, that's the magic trick behind all of this.
All right, so let's break down that whole sense and respond idea a little bit more.
At its core, it's actually super simple. It's a two-step dance. Step one, something in the environment changes. We call that the stimulus. Step two, the material does something about it. That's the response. It's a perfect cause and effect relationship that's literally built right into the material's DNA. And wow, the range of things these materials can react to is just huge. We're talking about everything from heat and cold, to pressure, to electric or magnetic fields, light, chemicals, even physical damage like a crack. By designing materials to react to these specific triggers, we can create some incredibly powerful new technologies. Okay, so we've got the basic principle down. Now let's meet some of the key players in this field. I like to think of them as different families, and each one has its own special talent for sensing and responding. First up, we've got piezoelectric materials. The name might sound a little complicated, but the idea is just beautiful. Basically, think of it as a material that can turn a squeeze into a tiny spark of electricity, and it works the other way around too. And this is absolutely crucial. It's a two-way street. If you apply mechanical stress, like you press on it or bend it, it generates an electric charge. But if you do the opposite and run electricity through it, the material physically changes its shape. It's this dual personality that makes it so unbelievably versatile. Next, let's meet the shape memory alloys, or SMAs for short. Honestly, the best way to think about these is like a magic paperclip. You could crumple it up into a little ball, but with just a little bit of heat, it would suddenly spring right back to its original perfect paperclip shape. It remembers. So what's the trick? Well, the most common stimulus here is a change in temperature. When the alloy gets warm enough, it triggers a change inside the metal that forces it back to a shape it was trained to remember. The undisputed rock star of this family is an alloy called nitinol, which is a mix of nickel and titanium. And this brings us right back to that cracked phone screen we were dreaming about just a minute ago. Self-healing materials are, well, they're exactly what they sound like. Materials that are designed to fix themselves when they get damaged. No help needed. But how on earth does that actually work? Well, one of the most common methods is just genius. The material is filled with millions of tiny microscopic capsules that are full of a liquid healing agent. Think of it like a special glue. When a crack forms, it breaks open the nearest capsules. That glue flows out, fills the crack, hardens, and bam, the damage is sealed. All right, these different families are cool on their own for sure, but their real power? It's in what we can actually build with them. Let's check out some real-world applications that are already changing our lives. This is where it all comes together. That same shape memory alloy we just talked about, nitinol, it's used in medical stunts that expand to the perfect shape using just your body heat, opening up a blocked artery. And the reason your phone knows to rotate its screen? That's thanks to a tiny piezoelectric accelerometer that's turning your movement into an electrical signal. This isn't future tech. It's in the devices we use every single day. And the power we're talking about here, it's just staggering. I want you to look at this number, 300%. What is that? Well, that's the amount of strain, or change in shape, that some of these electroactive polymers, often called artificial muscles, can achieve. That is an incredible amount of movement, and it's opening up wild possibilities in things like robotics and prosthetics. So you can see, this isn't just a collection of clever inventions. This represents a fundamental shift in how we think about engineering. We're moving from a world of passive objects to a world of truly adaptive systems. Looking at this timeline, you might be surprised. This has been a long time coming. The basic piezoelectric effect was actually discovered way back in 1880. But what's happening right now is this massive acceleration, where all these once separate discoveries are coming together to create unbelievably powerful new tech. And the future? Oh, the future is even more exciting. We are talking about 4D printing, where the fourth dimension is time, so we can print objects that literally transform themselves after they're made. We're looking at flexible, smart electronics woven right into our clothes, and adaptive materials that can change their basic properties, like how stiff or soft they are, completely on command. This quote right here, it really gets to the heart of the ultimate vision. We're moving beyond materials that just react. The goal is to create entire structures, a whole bridge, an entire airplane wing that can monitor their own health, anticipate when they're going to fail, and maybe, just maybe, even heal themselves. It's a leap from passive objects to active, self-aware systems. So I'll leave you with this one thought. As we engineer these incredible sense and respond behaviors directly into the very fabric of our world, the line between what is a simple material and what is a complex machine, well, that line starts to get very, very blurry. We are fundamentally redefining what it means to build our world.